trees. It's a medium level graph question. The question states a tree is an undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycles is a tree. Given a tree of n nodes labeled 0 to n1 and an array of n minus 1 edges, where edges I equals a, b, meaning like if this is a and this is b, there's an edge between them. Also, this is an undirected graph because it's trees. There's only exactly one path between nodes. As you can see, there's no direction in these edges. You can choose any node of the tree as the root. So as we can see in this example, all of these are connected in this way. 0 connects to 1, 1 connects to 2, 1 connects to 3. And there's so many ways we can represent this visually by just choosing a different root. So if we choose 0 as the root, it goes like this. And then if we choose 1 as the root, 1 has connection to all of these. So it's a tree like this. And then if 2 is the root, it's also like a tree with 2 levels. And 3 as the root, there's also like 2 levels. So ideally, this question is looking for minimum height trees, HTs. So we want to find the root, which is like 1 in this case, where it only has a height of 1. We're given input n equals 4. 4 is the number of nodes there are. Edges, it just tells you which node is connected to which node. 1 has a connection to 0, 1 connects to 2, and 1 connects to 3. And the output is 1 because 1 is the root of a tree that creates the minimum height of this tree. Yeah, so looking at this question, we can think that we're able to solve this using something similar to a topological sort. So 1 is the node with the most dependencies, and it has a dependency, it has an edge to all of these nodes. Like it has dependency to 0, it has dependency to 2, and it has dependency to 3. So basically, in topological sort, it goes like it uses a BFS way with a queue, and we first enqueue the nodes in the graph with the least dependencies. In this case, the least dependencies like could be 3, 0, 2. They all would go into our queue. We would enqueue 0, 3, 2 all at once in the beginning, and then 1 would be the last one to be enqueued. And in that case, 1 is the one with the most dependency. We can just output 1 in the very end. I'll explain it as I write the code. So we're gonna use a topological sort type of way to solve this. And to use topological sort, we normally have like an out degree, in degree, but out degree is basically just like similar to adjacency list. And to follow the traditional topological sort way, we'll also create in degree. But we can also get the in degree from our adjacency list by using, like, checking the length of how many nodes there are. To create the adjacency list, I'm going to use from collections import default dictionary. And then here, I'm just going to define my adjacency list, which is also like the out degree in topological sort. Adjacency list equals default dictionary. We can either use a default dictionary of a list or a set. I'm just going to use a set. A set doesn't allow duplicates. So after I define my adjacency list, I can also define an in degree equals. It's all going to be set to 0 as default because and initially we just say each node is like independent of itself before we assign them the edges. It has an in degree of 0, but for in this case, like 1 has an in degree of 3 because there's 3 nodes going to 1, and it doesn't have any directions. So each node, you know, if it's a tree, it's going to be connected in this graph. And if it's connected, it automatically has an in degree of 1. So this is a little bit different from the other topological questions where we start with nodes with in degree of 0. But for this question, minimum height trees, we should start with nodes that has an degree of 1 because everything is connected and there's like gonna be, I'll show you when I define the degree. So it's gonna be initialized as 0 as first, and let's populate our adjacency list in degree. So for node 1, node 2, we're gonna populate it from the given edges list to us. For node 1, node 2, and edges, adjacency list of node 1 dot add. We're using add because it's a function of set. Dot add node 2. We're gonna add it back and forth since it has no directions. Node 2 dot add node 1. And then same thing for degree. We're gonna increase the degree by 1 for both of these nodes. Node 1 degree plus equals 1. Then degree of node 2 plus equals 1. So after this, we know that for each node they're gonna have a min of degree of 1. So after we have to find this, we wanna create our queue because topological sort after all is using BFS. Queue equals, and we can populate our queue initially with all of the nodes with degree of 0. So we can do something like node for node, and we actually don't really need an degree. We can just do everything based off of adjacency list. Actually, I can try doing that. It saves us space. Node for node in the adjacency list. If length of adjacency list node equals to 1. So basically, we enqueue all the nodes in our adjacency list that has a length of 1, meaning we only added 1 node to it. It means it only has 1 degree. So we enqueue those first, and then for this question, I'm also going to create a count. There's a base case. So if n is smaller or equal to 2, then we can return. By the way, we can return a list of range n. By the way, these nodes are labeled from 0 to n minus 1. That's why we can just basically return the list of range n. Because if there's less than or 2 nodes for our tree, then that means either one can be the root, and that's why we return list of range n. And here we have a count. We have count equals to n, so how many nodes there are initially, and well, count is greater than 2. We can do, we can go through our nodes in our queue. So for node in queue, these initial nodes are the nodes with the least dependencies. We can look for the neighbors of it. So for node in queue, I'm gonna create a temp list for our temporary queue, and for node in queue, for neighbor and adjacency list of node, we can do adjacency list of neighbor dot remove node. So we already visited this node's neighbor, so we're gonna remove node from our adjacency list of our neighbor, so we don't visit our node again repeatedly later when we go through the neighbors of this neighbor. And we check if adjacency list, if the length of adjacency list neighbor now equals to 1, And then if it does, we append it to our temporary queue. And after that, we can decrease our count by 1. We've visited all of the neighbors in this node. We decrease our count by 1 because we fully visited this node. And then outside of this, if we visit everything in their queue and their neighbors, then now we paste whatever's in our temporary queue onto our queue. So queue equals temp. And then in the end, the nodes with the most dependencies are gonna be our root. So at most we can have 2 roots. And that's why after we exit this count, we can just return our queue. Whatever's left in our queue is gonna be the nodes with the highest dependencies. Let's try running our code. Yeah, so this is how I would solve this question using a topological sort with BFS. And the complexity would be O of V. V is the number of nodes in our tree. And then the space complexity at most for BFS is also going to be O of V. If we're unlucky, like everything gets enqueued at first, then it's going to be at most O of V nodes. Thank you so much for watching, and let me know if you have any questions.